We want to thank Google's Science Journal app for supporting PBS Digital Studios.
Black holes. They're weird. And a recent paper about them seems to me to be the strangest one yet. Black holes might be covered in hair. I'm Diana, you're watching Physics Girl, and it's been a while since I made a YouTube video, so I hope you're ready for me to get excited about space stuff. Let's get started. So, iconic theoretical physicist Stephen Hawking may have passed away in 2018, but papers he wrote are still coming out after his death. His latest paper, released in October, argues that black holes might be covered in soft hair. What does he mean by that? We're gonna get there by the end of this video, but first we're gonna understand what the heck a black hole is by doing a cool, weird demo that shows us intuitively why you cannot escape a black hole. According to Einstein's theory of relativity, the gravity of any given object is proportional to its density. So if an object is dense enough, then nothing that gets too close can ever escape, no matter what. Nothing, not even light, can escape from an ultra-dense object, so we would call that a black hole. Also, can we just take a moment to admire this black hole? My incredible animator made this. This isn't stock footage, this is a Physics Girl black hole, yo. That's all. Now, from the explanation of nothing being able to escape the gravity of a black hole, you might assume that gravity is a pulling force, and you'd be in good company. Sir Isaac Newton thought the same thing back in the 1600s. He noticed that when things move, they tend to move straight, unless a force acts on them and curves their path, a force like wind or a kick from Sir Isaac Newton. Newton then noticed that gravity also curves the path of things downwards, so he concluded that gravity must be a force. Einstein thought differently. He noticed a thing with an elevator. There was a moment he realized an elevator out in space accelerating up would act the same as gravity here on Earth. Basically, there was a problem with our theory of gravity as a force. So what is gravity then? Well, Einstein wondered, what if gravity isn't a force, but the curved trajectory of a ball flying through the air is actually straight? I'm gonna have to apologize in advance because the demo I'm gonna show you broke my brain just a little bit. Pretend you live near the equator and you start walking east, trying to walk as straight as possible on your initial path. You might think that you'd keep walking parallel to the equator and never hit it, right? Well, try testing this on a globe. Try it like this. Line up the edge of a piece of paper so it's parallel with a latitude line, and then keep pushing it down straight to simulate your straight path. And it'll actually end up intersecting with the equator. What? In fact, if you draw the latitude line you started on your paper and then flatten out the paper, that path would look curved as well. So your path actually curves because while you may be walking straight, the Earth you're walking on is not flat. No matter what any of those videos in the sidebar may tell you. That's what Einstein proposed, that gravity is not a force, but an object curves in a gravitational field for the exact same reason that your straight walking path ain't straight. Gravity is what happens when you're moving straight on a non-flat thing. Only in the case of gravity, that non-flat thing isn't the globe, it's space itself. And time. That's right. The fabric of the universe, space-time, is curved by large masses, just like the Earth's surface is curved. So let's bring it back to black holes. See, they're inescapable. As an object gets denser and denser, the stuff moving near it will take curvier and curvier paths. And then when you get to black hole level dense, the path an object takes gets so curved, it'll never ever lead back out of the black hole. And then it's gone, forever, without a trace. Not even a thank you note.